Good morning, students. Today I would like to take up with the lab session on RC phase shift oscillator, and that RC phase shift oscillator is designed by using multisim. In order to, the main concept of designing RC phase shift oscillator is application oriented in audio amplification. In order to deal with, let me share the screen of RC phase shift oscillator design. Let me share the design of RC phase shift oscillator. Uh, Basically, RC phase shift oscillator is an audio frequency oscillator, and it is constructed by using fundamental components R and C in the feedback element, in the feedback. This RC phase shift oscillator mainly used for voice synthesis. It is mainly used for GPS voice. Almost the main application is audio amplification. Next, the content I would like to deal with respect to RC phase shift oscillator are introduction, working principle of oscillator, circuit diagram, how we are implementing the RC phase shift oscillator, and design procedure as well as outputs from multisim I need to discuss. Basically, RC phase shift oscillator uses resistor and capacitor network to provide a phase shift required by the feedback signal. They have excellent frequency stability and produces pure sine wave for a wide range of applications. Ideally, one simple RC network produces a phase shift of 90 degrees, and practically we can design for our desired frequency or our designed phase shift. In this RC phase shift, we are designing each RC network for 60 degree. Therefore, to yield 180 degree phase shift, we need to use 3 such RC networks. Basically, in order to start with RC phase shift oscillator, first before going to deal with that, I need to talk about the working principle of oscillator. Basically, oscillator it works with positive feedback. It consists of amplifier part and feedback part. Amplifier part is designed by using here BJT, and feedback part is designed by using RC combination. Therefore, this circuit is called as RC phase shift oscillator. Basically, the important criteria need to satisfy to get the oscillations are two criteria need to satisfy. They are called by the name Barkhausian criteria. Number one, the modulus or product of gain in the sense A is the gain of amplifier part and beta is the feedback factor. The product of A into beta should be equal to. Basically, R into C, it gives a phase shift of 180 degree. Amplifier part gives a phase shift of 180 degree, and feedback part gives a phase shift of 180 degree. Total phase shift of the loop is 360 degree. Two Barkhausian criteria it need to satisfy. Now, number one, first criteria is the product of A into beta should be equal to unity. A is the amplifier gain and beta is the feedback factor. And total phase shift around the loop should be equal to 0 degree or 360 degree. Here, amplifier part, if it is giving a phase shift of 180 degree, remaining 180 degree phase shift should be produced by feedback part. These are the two important criteria need to satisfy by oscillator circuit to get the sustained oscillations. This is the circuit diagram of our RC phase shift oscillator. Here, this particular part, this part is your amplifier block and this part is feedback part. Since it's a BJT amplifier, common emitter BJT amplifier, this produces a phase shift of 180 degree and remaining 180 degree phase shift need to produce by feedback part. Among 180 degree, each RC network produces a phase shift of 60 degree. Three such networks use us to produces a phase shift of 180 degree. Therefore, total phase shift around the loop is equal to 360 degree, which satisfies the Barkhausian criteria. This is the circuit diagram of your RC phase shift oscillator. In order to design the RC phase shift oscillator, the design procedure is first I need to design the amplifier part, then I need to design the feedback part. To design the RC, that is amplifier part and the feedback part, the given parameters are, these are the given parameters from the data sheet. From the data sheet I got these are the design specification. To start with this, I'm from the oscillator part, from the amplifier part. From the amplifier part, I need to design RC, RE, R1, R2. R1 and R2 are the resistors of feedback, that is voltage divider method of bias. RE is the resistor associated with emitter. RC is the resistor associated with collector. We need to design these resistors one by one. To design these resistors, to start with, I'm starting with a resistor design of emitter resistance. RE is given by VE by IE. RE can be given by VE. VE can be assumed as it is 1/10 of VCC or 1/6 of VCC, like that. Here we have taken VCC is equal to 12 volts. Here I assume VE is equal to 1/6 of VCC. Therefore, 12 by 6, which is equal to 2 volts. RE I can calculate by using 2 volts divided by 4 milliampere. Where 4 milliampere is the quiescent current, collector current. Therefore, I got the value of RE as 500 ohms. Approximate nearest resistance available in the lab, it is nearly about 470 ohm. Next time I need to calculate the collector resistance. To calculate the collector resistance, I need to apply KVL. I need to apply KVL to this outer loop. If I apply KVL to this outer loop, VCC minus ICRC minus VCE minus IERE equal to 0. Therefore, IERE equal to 0. Then I'll substitute all the values. VCC equal to ICRC plus VCEQ plus VEQ. If I substitute all the values, I got the value of RC is equal to 1 kilo ohm. Now I need to design the voltage divider method of biasing. To design the voltage divider method of biasing, first I'll calculate VB. To calculate this VB, let me apply the divider formula. Voltage divider formula is main voltage, resistance of the branch where I am calculating the voltage, divided by total resistance. I got VB value is equal to 2.6 volts. VCC I already know. R2 I assumed R1 as 36K, and I can calculate the other one R2 as 10K. This is how the design of voltage divider method of biasing continues. Step 4 deals with the design of capacitors. Here I'll assume all the capacitors are of value 0.47 microfarad or 0.1 microfarad depending on the frequency I deal. Next, this is the design procedure of amplifier block. Basically, oscillator will have two blocks. One is amplifier block, another one is the oscillator block. These are the design procedure amplifier block. Next, I'll deal the design procedure of feedback part. To design the feedback part, here each RC network will give the phase shift ideally equal to 90 degree, but here each RC network is designed to give a phase shift of 60 degree. Therefore, 3 such networks are used to get a total phase shift of 180 degree. Remaining 180 degree is produced by common emitter BJT amplifier. In order to design this feedback network, the frequency formula is given by this. Here, frequency of interest is 450 Hz or 1 kHz depending on audio frequency range. Here I'll assume C value as capacitor value as 15.9 nanofarad, and I calculated the R value, which is nearly about 10 kilo ohm. This is the procedure of my RC phase shift oscillator feedback part design. Then next, this is the output waveform of my RC phase shift oscillator, and this clearly indicates that I am getting a frequency of my 500 Hz nearly. In order to deal with what are the application part, it is basically used as an audio amplifier. It is used in musical instruments. It is used for voice synthesis as well as GPS units in modern days. Now, to check how this RC phase shift oscillator works, or how this particular RC phase shift oscillator is working in multisim. This is the circuit I connected by dragging and dropping of all the components from the circuit, from this component list. I made the circuit. Here it is open. So let me place wire and let me close this. Let me close the circuit. Now, this is the circuit. I took components from the list. I connected this circuit. Now, let me run this circuit. If I see the output waveform, see, my frequency is generated. frequencies generated. So, this is how we'll get the RC phase shift oscillator output using multisim. Main application, as already we discussed, it is used in audio amplification. Thank you very much for your patience listening.